Alright, so this is going to be kind of a fun video. It's a cloudy night, so we're going to learn about astrophotography pre-processing using this cartoon galaxy. Simulate taking it with a low resolution monochrome camera, and we'll add to it all of the kind of real world noise that you would see in an astrophoto. We'll learn about pre-processing using calibration and integration to remove some of this noise. So the real beauty of using this synthetic data, which was just produced in Photoshop, is layers added on top of a perfect image. Just a perfect rasterization of this infinite resolution vector graphics, is that we can control the noise and we can deal with it independently and experiment and have fun with this. So the first kind of noise that we deal with is purely random noise. So you can see there's a satellite in the upper right corner. It's a random event. And there's just a random distribution of speckles of pixels. And we can learn to get rid of that. So the satellite's gone and most of the noise is gone. There still remains some other noise though, and this is bias. So this is just flaws in the sensor. It looks like a random distribution, but it's actually consistent. And a different type of noise in addition to that is thermal noise that accumulates over time, shows up as a glow from the top edge and from the lower right edge, and also a random looking distribution, but that's consistent. We'll learn to get rid of both of those and have a nice clean image. It still has some problems though. There's vignetting around the edges, there's dust motes in the center very clearly, maybe smudges on the filters, things like that. We'll learn to model that and get rid of that as well. So let's get started. So starting with random noise, that's super prevalent, super pervasive throughout all of our photos, but it's actually one of the easiest things to deal with. You just take a lot of photos and stack them. So the idea is that you're averaging away this random noise. So if we take these into PixInsight and blink them, it's pretty clear. You can see there's some strong signal there, but it just has a bunch of random speckling of noise thrown into it. And this is simulated in Photoshop, of course. There's no way you'd get something even this clean in the real world. Another thing is some of these random events, like here's a meteor in one frame. Now you could just drop that frame. You could use pixel rejection algorithms to remove just the pixels from that frame. Here we'll just simply integrate, which is basically just averaging the frames together. The idea is that, for example, the meteor is in only 1 out of the 30 images, so averaging them together makes it 1/30th as bright. Same thing with all the random noise. We do this and we end up with a very clean image. You can slightly see some noise in there, but it's reduced about as much as possible. If only we could be so lucky in the real world to have images that have only random noise in them. We could get rid of it just through integration. But in the real world we also have systematic noise, which is consistently hot or cold pixels because of flaws in the sensor. This is the bias here. You can kind of see a stripe in the first quarter of the image, vertical stripe, and also some randomness there. Another type is thermal noise, which depends on the length of the exposure and the temperature of the sensor. It shows up also as kind of a random distribution of pixels, but they're consistent. Or as a glow, like it does here from the top and the bottom right. It depends on the sensor. If we take that into PixInsight and blink them, you can kind of visually see the separation between the random and the systematic noise. A bunch of noisy looking pixels, but some of them aren't moving. Now if we just apply the same technique as before and just integrate these frames, we'll see how well that works, but I'm expecting that to essentially remove the truly random noise, which cleans it up some. It's a little bit better. But it's not going to remove the systematic noise because that's not moving, and so it accumulates along with the signal. There is a technique though where in between each frame that you take, you move the telescope a little bit. That's called dithering. And the purpose then is that if you blink that, you see that the subject is moving in the frame, but the systematic noise is staying still. So you can very easily visually separate that. If we can visually separate it, we should be able to algorithmically separate it. And so one really cool thing to try is to take these frames and do star alignment on them. And the result is that you have a subject that then remains still, but the systematic noise moves around because the actual frame of the sensor has been moved around. So look at that. It looks just like a dirty piece of glass sliding around on top of our subject. That should be fairly easy to separate, especially now that this systematic noise is moving around a bit. We can integrate that, and that noise will be smudged. You know, it's not quite as effective as if it were random, because there is a pattern to it and it's just being smudged around, but it reduces the noise significantly. We'll come up with other techniques to deal with systematic noise, but no matter what we do, there will always in the real world be some residual systematic noise, and dithering is a great final step to remove whatever residual noise we weren't able to remove otherwise. So that looks pretty good. It's a little bit noisy. You can kind of see a smudge of a pattern of pixels in there. If we took more images or we dithered a little more drastically, that could have helped. But a better idea is to just take darks, which is essentially a picture of the thermal and bias noise. So now if you just cover the telescope, cover the camera, take pictures in complete darkness, then you should get a picture of the systematic noise. Now it's important that you take these at the same gain or ISO, the same length of exposure, and most importantly the same temperature as your light frames, so that you're getting the same systematic noise that you have in those light frames. But here you can see there's a bunch of random noise also mixed with that systematic noise, and of course we know what to do with that by now. We just integrate it, and that will get rid of the randomness, and we'll be left with a picture purely of the systematic noise. That looks pretty good. And what we can do now with this so-called master dark is subtract it from our light frames. So this is a nice portrait of the noise model of this camera. It'll be different across different cameras, but if we subtract this now from our light frames, we should get a clean frame. So that's the formula. Lights minus darks gives you a clean frame. So we take our lights again in the calibration tool. This time we apply this master dark to it, which will subtract it from each of them, producing a whole new set of calibrated images now. And if we take those calibrated images and star align them, which is very similar to what we did before with the uncalibrated ones, only last time with the uncalibrated ones, when we blinked that, you could kind of see this dirty window effect sliding over the image. This time you won't see that, because that kind of noise has been removed. Instead, we're left with just the random noise. You can't really see much systematic noise in here. Maybe if you look closely, there's a little bit of residual. Actually, there's a hot pixel or a cold pixel there in the core of the galaxy. You can kind of clearly see. It's a little bit reduced though. Also, this is a little bit wobbly. The star alignment's not working so well with this synthesized super low resolution blocky stars data, but good enough for this demo. Of course, integration is our friend for getting rid of the random noise. We integrate all of these frames and we end up with a rather astonishingly noise-free image, given what we started with. So this has worked out quite well to produce a pretty noise-free image from an incredibly noisy image. Just characterizing the systematic noise and integrating away the random noise, we end up with this beautiful thing. Now, in the real world, we will end up with some other problems due to the optics. These are gradients across the field. This will include vignetting, where the image projection circle isn't evenly covering the sensor, maybe dust motes on the lenses or mirrors or on the sensor itself, maybe smudges on the filters. And we essentially want to get a portrait of those problems and use it as a calibration frame, just like we did with the darks. This we call flats. And so with flats, we're trying to get a picture of the inside of the optical train. We want to do this with a nice, evenly lit field. So one technique people use is just put a white t-shirt over the telescope along with an iPad and take pretty short exposures, long enough to expose maybe the bottom third or so of the histogram, but not long enough definitely to clip any of the pixels. And if we take this into PixInsight, we'll see that it looks a lot like a deep sky object photo with a bunch of noise, systematic and random. And we can apply some of the same techniques, average away the random noise, and then characterize the systematic noise. Now to characterize the systematic noise, it's the same exact process. It's darks again, only this time it's much shorter exposure time. We call those dark flats. So the formula is flats minus dark flats. So dark flats really are, exposures in the hundredths of a second kind of time range rather than hundreds of seconds. they end up accumulating a lot less or almost no thermal noise, and so it's essentially a picture of just the bias. A lot of people actually just call these bias frames. Sometimes people literally take images at the shortest possible exposure time to capture only bias. But here we'll take what we're calling dark flats. Darks, just like the other darks, only they're at the exposure time of the flats. So here's a good flat dark that's been integrated to get rid of the random noise, and it's just a picture of only the systematic noise. And so just like we did with the deep sky objects, we will use this to calibrate the flat frames. So go back to calibration, apply this as our master dark, and get a bunch of calibrated frames, integrate those to get rid of the random noise, and voila, we have a nice calibrated flat frame. Interestingly, we're going to do a pixel-wise division using this flat frame to get our final corrected results. So the complete formula is lights minus darks over flats minus dark flats. Now normally we would do this whole process in a scripted way in PixInsight. Everything we've shown is not really the way you would do it, and this especially is not really how you would do it. I just thought it would be fun to use pixel math with just a single frame and see the results very directly. So we can kind of prove that this is the formula indeed to get nice clean images. So there's our light and our dark. And so then here next is our flat and our flat dark. It's kind of interesting to notice that the difference between the dark and the flat dark, because of the exposure time, the regular dark has a lot more thermal noise, has this glow, and actually has a lot more background noise to it. But using pixel math, we can now work with these images. They're all named, so we can just refer to them by name. So let's start with light minus dark, and that'll give us a nice clean light frame, removing the remaining systematic noise. It still has some vignetting, of course, and the dust motes and whatnot. So next we'll do the same with our flat to get a nice clean flat. So it's flat minus dark flat. And there's our clean dark flat. And of course this data is coming out perfectly because we're using this synthesized data from Photoshop. So in the real world, none of these turn out quite so noise-free. Then finally, if we divide the two, we get our final result. Now the way division works is, if you imagine normalizing the flat frame so that white is 1, well, anything that's white then will have no effect. X over 1 is just X. But anything darker than that will have an amplifying effect. So 0.5, for example, would double the pixels in the light frame. So that's how pixel division ends up doing what we want. There's our final image. It looks quite noise-free. Of course, in the real world, we would do this again for red, green, and blue so we can get color, maybe even hydrogen alpha, and we'd end up with our beautiful color image in the end. So hopefully you found this fun, maybe kind of a novel way to learn about pre-processing. Hopefully we'll get some clear skies and we can go gather some real data. Have fun.